Your kind attention on behalf of ICTS and Jawaharlal Nehru Planetarium, I extend a very warm welcome to you all. Those of you who have joined us offline here, as well as those who have joined us online to this edition of KAAPI with Curiosity. I extend a very warm welcome to the speaker of the day, Professor Swapan Chattopadhyay, who is going to speak to us on a very interesting topic, beaming into matter and life with particles and light. Very poetically worded title. Look forward to this, sir. So, hearty welcome to you. Yes, I request Professor Vijay Kumar of ICTS to use the speaker to the audience.
Thank you. Welcome everyone on behalf of ICTS as well. So it's a pleasure to have Professor Swapan Chattopadhyay speaking in the KAAPI with Curiosity series today. So Professor Chattopadhyay did his undergraduate education at St. Xavier's College, Calcutta, MSc from IIT Kharagpur in physics at the Fermi National Accelerator Lab. There's a long list and I don't want to embarrass him more. I should just end by saying he's also well decorated for his work. He's a fellow of the American Physical Society, the American Academy of Arts and Sciences, the Institute of Physics, the Royal Society of Arts, and also the corresponding fellow of the Royal Society of Edinburgh. So it's a great pleasure to have him here to speak to us about this wonderful topic. So I hand over the chair to Swapan.
Okay, so that's great. Can you all hear me? Yeah? I have to decide which side I should probably have to do that. Thank you all for coming on this beautiful Sunday and sparing a couple of hours to be here. It's outdoors at least. I'm told that the main auditorium is being worked on, so they put this together, which is nice. Ceiling fans are on, so it should be comfortable, I think. So, yes, thanks. So let me first give some acknowledgement. So I must thank Rukmini, who is not here. She just came back from Calcutta, and she wrote to me apologetically. So Vijay introduced me, but she invited me to give this public talk. And I also want to thank Madhusudan and the leadership of this Jawaharlal Nehru Planetarium for hosting me. And finally, I'm in Bangalore now since September, thanks to Infosys Foundation, which allows me to be an Infosys chair at IISc Bangalore, and also Rajesh Gopakumar, who had appointed me an adjunct professor there. So it has been wonderful for the last 3 months. I'm here till December 11th, but I'm glad this thing came in the right time for me just before I leave. So let me start with a little bit of a personal reflection. If you can, I don't know whether you recognize where this place is on Earth. Can anybody say where it is? Is it in India? Is it outside India? Anybody in the audience? No idea? So this happens to be Darjeeling, at 7,000 feet altitude. In the backdrop, you see the Kanchenjunga. It's in the border of Nepal, Sikkim, Bangladesh, and India. Actually, this was my boyhood up until early 1960s when all the trouble broke out with India-China conflict and Dalai Lama fleeing, all of that. So I grew up in this beautiful little town, not a village, it's a big town actually. And I actually had 2 very significant experiences there. So because it's a mountain town, it's very popular for mountaineering. It's also very popular for tea gardens, and it is popular for tourists. So Tenzing Norgay and Edmund Hillary climbed Mount Everest in 1954. So Indian government and New Zealand government created a Himalayan Mountaineering Institute in Darjeeling. And I was one of so I experienced training there, and I'll tell you from who. And I also observed in 1959, the Sputnik, you could see everybody with their telescope looking in the sky with this little artificial thing going in the sky. I could see barely with my open eyes. So I was one of the first 6 kids that got actually handheld mountaineering lessons from Sir Edmund Hillary and Tenzing Norgay. All the adults were scared out of their blues to take this class, but we were so young, we just took it. It was fantastic. The second thing was I also got to know at that time, the Sputnik thing really made my mind turn, and later on I read about Lord Ernest Rutherford, who was also another New Zealander. I'll talk about him later, and his two students, Cockcroft and Walton. I actually had the fortune to hold a chair, a professorship in England in the name of Sir John Cockcroft. So these two guys split the atom, and I would say the very first application of accelerators to study structure of matter and particle physics and nuclear physics started in 1932. So in the left, you see Walton, in the right, Cockcroft, and this is Mr. Ernest Rutherford from New Zealand. So what did Rutherford do? He actually, in those days, people did not know what matter is made of. They thought it is some kind of a substance, maybe like a plum pudding. They had no idea what kind of internal structure it is. So Mr. Rutherford was at Manchester at the time, and he put a little gold foil, and he shot atoms of helium at this foil, and he saw that most of the time they went through. So there's a lot of empty space, but occasionally they bounced back very hard in a ricochet. And that immediately told them that the actual matter inside objects, nuclear matter, is more like a plum rather than a plum pudding. There is a hard seed inside, which we today call nucleus, and outside there's a fuzzy electronic ball, something. So he did this in 1909, and then of course his students immediately, in about another 22 years or so later, took a lithium atom and sent in a helium beam and split the atom into two. And when you add up the energy and mass, they proved E equals mc squared, Einstein's famous equation that matter and energy are equivalent in a system of a lithium atom. And then today, of course, with beams of particles, we know that if you look at any matter, if you look at the very fundamental element, hydrogen, you ionize it, you get a nucleus, which is a proton. Inside a proton, there are three little things. We call them quarks. And they are oscillating back and forth, interacting with each other. There's the energy field inside. If you look at the weight or mass of the three particles, it's very, very small compared to the weight or mass of the entire proton. So most of the mass or heaviness of the proton is coming not from these three particles. It's coming from the energy exchange between these three particles inside the nucleus. So that energy can be interpreted as mass. It's a gluons, they call it technically. And so it is the energy in the proton that appears as the mass of the proton. So all this actually throughout, from the 1920s, Cockcroft and Walton, 1931, 32, to Lawrence, starting from a 1 meter little device to prepare a beam to crack an atom, all the way throughout the 20th century, got bigger and bigger and bigger, and then you saw this large 27-kilometer large Hadron Collider, which discovered the Higgs boson. It had to get big because you had to get higher and higher energy particles to probe shorter and shorter distances. So it's like a microscope. If you want to look at smaller organisms, you have to use light of shorter wavelength. And so today, of course, so you see the between 1 meter to 27 kilometers, big jump. And today, the very last accelerator was this large 27-kilometer thing, which in 2012 discovered the last element that was unknown of matter. That's called the Higgs boson. And so now the people are asking what is next. But before I go to that, let me just tell you why. Why are we going into this game of producing higher and higher energy particle beams to probe matter? And this is something that I should tell you, that we are, of course, the birth of modern science kind of started throughout up until Galileo's time, but he actually put it into concrete scientific terms, that you should measure whatever is measurable by your existing tools. And you should make measurable what you think is not measurable today. So you must measure things and verify your understanding of the world. And so this was then echoed 200 years later by this gentleman called, named Sir Humphrey Davy, who said that nothing tends so much to the advancement of knowledge as the application of a new instrument. So you need an instrument to measure anything in order to form an ontology or a metaphor of how the world looks like. And of course, famous theoretical physicist Freeman Dyson, he could say it because he was a famous theoretician. He said that new directions in science are launched much more by new tools than by new concepts. Not quite true. He was being very modest, and he wanted to give credit to the experimentalists. But it is true that we play a game of back and forth. Theory proposes something, experiment proves it, but tools are essential, and tools are there to measure things that you think you should measure. So there's Galileo's telescopes. He was trying to be smart and convince the royalty that they should give him more money so he could make a much bigger telescope. Okay? And by the way, Galileo always kept 10% of the money he got from the king for the lens grinder, because he always showed the lens grinder what he's seeing up in the heavens. And he got excited and said, okay, I got 10% of my income, I give it to you, can you make a bigger lens? And of course he would make it, because he would get to see through it. So he's a very clever man. Then of course you have Newton's prism spectrometer and microscope and all of that. And today you have these large things. You got this large facility in Geneva, in Hamburg, in England, and here in China, in India also. There are synchrotrons, and it's all over the world. And basically what these are trying to do, if you look in the scale of things in nature, you look at radio telescopes and other telescopes to look at galaxies and stuff. You look with telescopes and things to look at solar system. You use telescopes, binoculars, cameras to look at human-sized things, mountain peaks, humans, and the Earth, and so on. And you look at a microscope to look at organisms and biology. You look at lasers to look at atoms and molecules. And then you go into particle beams, which can generate much shorter wavelengths of energy to actually look into objects which are much smaller, like nucleus and things within the nucleus, things within a nucleus, within the nucleus, and so on and so forth. So that's an order of magnitude, 40 orders of magnitude, 10 to the minus 18 to 10 to the 21. That's 40 orders of magnitude you're spanning in your observation and measurement. So these are the instruments. This is why we build for some things, like in this end, you got to build things that are very large to get the energy you need to see things. At this end, you want to see large objects in space, so you need other observational techniques. And if you look at nature's time scales, we talk about the scale of things in size, and there's vibrations everywhere in nature. If you look at a solid, inside there are vibrations, which you call them phonons, not photons, phonons. They are like sound-like vibrations, acoustic vibrations, and they typically go at a microsecond, millisecond, sometimes nanoseconds. And then, of course, you have dynamics of electrons going around atoms, and these are typically picoseconds and femtoseconds, sometimes attoseconds when you go to the very simple dynamics of electrons moving around, buzzing around an atom. And then, of course, you go into particle collisions and cosmology and strings and very high energy. And these are actually going at 10 to the minus 24. So I had to remember, you go from second to milli, to micro, to nano, to pico, to femto, to atto, to zepto, to yacto, which is 10 to the minus 24, to something. So that picture I showed you, the quarks going within a nucleus, they are going at 10 to the minus 31 seconds time period, very, very fast. Someday, we will have a microscope that can look at the oscillation of the quarks within a proton at 10 to the minus 31 second period vibrations. Not today. We cannot do it today. And of course, all these scales of nature, time and space, is reflected in our current understanding of the universe that we know, that came to be about 13.8 billion years ago. That's just a projection, because we know it's expanding at a certain rate, and you project it back, it goes back to 13.8 billion years ago, where something crazy must have happened. Some energy density was so high, the whole idea of space and time must have emerged from that point. And you see all the time scales. You see these wave fronts pictured after 300,000 years after the Big Bang. You could not see any light coming out of it because entire matter was so polarized like a plasma. And if you shine a laser beam onto your tube, when you don't see them going through the plasma until you make them neutral. When things become neutral, then light comes out. So it took 300,000 years for the matter, hot matter in the primordial universe to become neutral, and then light comes out. So you can see cosmic microwave background radiation, but that goes back only up to 300,000 years since the Big Bang, not before. If you want to look before, you have to maybe neutrino beams. I'll talk to you later about that. But the most important object is that this guy, there must have been tremors of space-time created by the Big Bang. So the tremors in space-time is still there. I mean, I'm here, you guys are there a few meters, but it's not fixed. It's fluctuating at a certain level, 10 to the minus 21 delta L over L, at a certain frequency, maybe a millihertz or something. So if you can measure that in a laboratory, you know a lot about the start of the universe at that point. So I'm going to now describe to you how we have gotten to this level of understanding with beams, particle beams and light beams. So I will describe to you by going on this thing, and then I'll tell you the instruments are basically particle beam accelerators or lasers made from particle beams or atomic beams. And then I'll also tell you it took a large number of people, scientists, engineers, students, postdocs, society, countries to fund it. The collaboration was very important, and not all parties are equally empowered. You know, there are poor countries, rich countries, but it all worked together in a new way of collaborating in society, and I'll tell you a little bit about that. Not everything is done by individuals sitting on a desk, but I mean, many people's things are done, but these kinds of things require a lot of people. So I'll say that. Okay, so if you look at a beam, many people ask me, well, what is a beam? If you look at a dictionary of a beam in a dictionary is all kinds of things, but there's little two lines saying it's maybe a ray of light or a bunch of particles going very close to each other in a parallel thing. But I can tell you that a beam is nothing but a directed flow of energy and information. Energy can be carried by particles, atoms, molecules, electrons, protons, and wave and information can be also carried by waves, radio waves, electromagnetic waves, optical waves, and so on. And you can actually look, let's say you look at a beam of light, laser. I'm showing you a picture of a ray of light from the California Livermore Valley. It looks very benign, goes all up to skyshine. But if you look closely inside the actual structure of light inside this laser beam, a lot of dynamics going on depending on the coherent state of the photons of light that are making up this laser beam. Long time ago, famous scientists from Bangalore and India, Sudarshan, worked out together with Glauber, Roy Glauber from Harvard, what is the quantum state of light in this beam. It's called Glauber-Sudarshan model of the coherent state of a laser. It's a very complicated thing. In general, you can actually, in general, you can paint a beam in its phase space by simply some kind of a combinatorial game with classical physics, or in quantum mechanics, you can play all kinds of quantum games to paint the phase space of the beam so it looks different from time to time as you want to paint it. So this information content of the beam is heavily used in creating very high energy particles, and then you collide them, so the energy gets converted into pure energy. These particles coming in, colliding, pure energy, and then of course you can nucleate into all kinds of matter. The energy content of it also is used because the particles have quantum numbers, their properties, characters. So whatever comes out depends on the intrinsic properties of the particles. But more classically, when you create a beam of light, you can paint light differently, as I showed you the laser beam. So the information aspect of a beam is heavily utilized by beams of light called photon beams or light beams. There are many accelerators producing tailored light, exotic light that you cannot get in nature. So I'll give you examples of these. That is very heavily used in photon sciences. Energy aspect is used in particle physics and astrophysics. Okay. So typically, you get very heavy, high energy TeV, 10 to the 12 electron volts of proton, and you have to bend them by radio frequency electromagnetic field. So you design very special cavities, electromagnetic cavities, that have a field that can deflect a TeV proton slightly, so you can actually bend them. You can make them come and become like a crab-like, then they cross, so you get a very high probability of collision of these two particles. So when they collide, particles in one beam collide with all the particles in the other beam, and then you get some event that comes out of it. Okay. So how do we make these beams? Well, you learn from nature. If you look at the Crab Nebula carefully, you see a beautiful light that comes out. And this light is coming out because there's a plasma and there's electrons which are being affected by magnetic field. Whenever there's a magnetic field and the electron gets bent, when a charge gets bent, it emits light. Depending on how strong the magnetic field is, how strongly it bends, whether it's periodic magnetic field, then it emits a periodic light of a certain frequency. So you learn from it that radiation comes from accelerated charges, and you also know, looking at a butterfly, that when you diffract light, you see a periodic pattern. So almost all particle accelerators, we have to produce in the laboratory a periodic structure that if you power it with electromagnetic power from the source, it generates an electric field that can accelerate a beam, or you can actually also allow that beam to radiate into the structure like a butterfly. So acceleration and radiation are just kind of reciprocal objects. They go together. If you don't have any radiation, you have no acceleration. If you have no acceleration, you have no radiation. So after about 90 years of looking at it, people came to learn about this in the 1930s and started to produce synthetically in a laboratory periodic structures of magnetic field and electric fields that can mimic what's happening out there in space. And so these are some pictures of linear accelerators. Okay, so so now I'll give an example of a typical accelerator so you know how it works. This is called a superconducting linear accelerator. It's based on these cavities, periodic structures that you actually create, but this is superconducting. And let me explain what superconductivity is in very simple terms. So superconductivity was discovered by accident by this gentleman, Cameron Lingons, in 1911. He was studying mercury and its electric properties. Most metals have electrical resistance. When you send current through it, it does not go far. The thing gets hot because it's dissipating energy. On mercury, he cooled it, and at a certain point, suddenly it seems to have lost most of its resistivity, and it becomes almost infinitely conducting. And later on, people started to understand superconductivity and created all kinds of type 1, type 2, type 3 superconductors. We use superconductivity in particle beams for two reasons. One, if you simply look at a microwave cavity and you put energy into it, it sloshes back and forth for a length of time, and then it dissipates and damps and heats up the wall, and then you have to stop for a while until it gets cold. And then again you inject energy into it, and it heats up the wall, and then you cool down. So it's pulsed. It's pulsed. You cannot just continuously operate ordinary cavity surrounded by copper, aluminum, or ordinary metal in a continuous mode. If you now look at a cavity made of a superconductor, like a niobium or aluminum, something like that. If you put in a burst of energy into it, it keeps on ringing and sloshing forever. So you can imagine putting very specific charges, electrons, protons into it, and it keeps on getting accelerated for a long length of time. There's a continuous acceleration of particles in it. Give you an example, just a movie. I hope it works. This you see niobium cavities, many, many cells. You have studied in maybe in high school or in college that these can trap electromagnetic energy, and you of course have to roll it up into insulating material. These are at 1.9 degrees Kelvin. So these are minus 271 degrees Celsius. So cold. At this temperature, niobium becomes extremely superconducting. You put jackets around it to keep the isolation of heat loss or heat penetration into it, and you create a jacketed module which can contain this electromagnetic field inside the niobium cavities. It's called a cryomodule. It's probably worth 100 million electron volts of energy. And you take a metal and you shine laser beam on it, you get photoelectric effect, it gives you electrons or charged particles, inject into these cavities, and of course it senses the electromagnetic field that you have trapped into it. It keeps on getting accelerated faster and faster and faster and faster. Up to a certain point, it reaches almost the speed of light. Beyond that point, it does not really gain any more energy, any more speed, but it keeps on gaining energy from GeV to 10 GeV to 100 GeV to 1000 GeV to 1 TeV at speed of light, and it's a bunch of electrons. Whenever you have an electromagnetic field which is longitudinal, it comes with a magnetic field around it. E and B are perpendicular. Maxwell told us this some 170 years ago. So that magnetic field tends to focus the beam. So you are doing two things. You are accelerating the beam by this electric field, but also there's a bunch of particles which see the magnetic field around the electric field, which also gets focused. The more you focus a beam, the more you're making it compact and colder. That means the information content is very dense. Entropy of the beam is going down thermodynamically. So this, of course, has been exploited from 1920s to 2012, and the latest hurrah was in 2012 when he discovered the prized particle, Higgs boson, Nobel Prize, people cheering. Theory was given in 1964, design of this collider was in 1984, and construction started in 1990. Finally, it's almost like a 50-year game. It was amazing. So a large number of people from 1920 to 2020. Many of them are Nobel Prize winning physicists, many fantastic engineers, students, postdocs. People have actually worked on this, keeps on switching. Of course, there's world news, but it took this 100 years to actually, what we know fundamentally, what is at the bottom of ordinary matter and energy that we see around the world. And basically, it is 17 constituents. So 6 of them are 6 types of quarks: up, down, charm, strange, top, bottom. 3 types of charged particles. They look like electrons, but there's slightly heavier electron called muon, slightly heavier muon called tau. 3 types of very funny, strange particles called neutrinos, so that's 12. Then there are these photon, W and Z, boson and glue. These are particles, but they mainly mediate forces between particles: electric force, magnetic force, strong force, weak force that makes particles decay and so on. And squarely in the middle sits the Higgs boson, which is supposed to give existence, mass, weight, gravity to all the other particles. Okay, so it's a bit more complicated than this because there's 8 types of gluons, there's W plus, W minus. Each particle has an antiparticle. So in reality, there's 50 or 51 or so. But this is the essence of Standard Model. I call it a mandala because I grew up in Darjeeling, Tibet, Nepal, Sikkim. They love mandalas. It's a beautiful creation. I call it a Standard Model mandala of particle physics. And basically, this is it. We know everything here except 2. Higgs, which was just discovered in 2012, and these 3 guys called neutrinos. Okay? So the Higgs is a very funny particle. It is responsible for the existence of mass or substance in each particle, and yet we really do not know what it is. It sits in the landscape of other particles energetically, very precariously. And the neutrino is a funny particle, like it is very shy to reveal its identity. If a neutrino goes from here, you see a face, the face. So neutrino comes in 3 types of flavors. And they constantly keep on changing their flavor as you catch it. It's called flavor oscillation of the neutrino. So this is a kabuki game they constantly play. It's very hard to pin down where this dynamics is coming from, how it all works. So to understand the neutrino, of course, people are studying it from all sources. Radioactivity gives neutrinos. You have reactors. Nuclear reactors produce neutrinos. You have accelerators, like I described, produce neutrinos. You have from the sun, million electron volt kind of energetic neutrinos. You have atmospheric neutrinos coming from atmosphere. You have supernovae exploding up in space, and you see very high energy neutrinos. You have from the Earth, from the core of the Earth, there's neutrino coming up. Then you have, of course, Big Bang from the 13.8 billion years ago, very, very low energy neutrinos. So actually neutrinos can be seen to probe the Big Bang if you have low enough energy to probe it. And then finally, the huge TeV energy neutrinos coming from this extragalactic, they come jets of neutrinos coming in. So people are looking at neutrinos all over the world by various techniques. And to understand the Higgs, people are proposing even preposterous, ridiculous accelerators, like you can say 100-kilometer diameter accelerator. It's called FCC, Future Circular Colliders. It's a lab based on superconducting magnets and cavities. We do not know whether it will ever come to existence or not. It challenges the geopolitical relationship, the financial stability of a country, and collaboration and across the globe. So, but these are the two, the Higgs and the neutrinos, people are working on at present. Okay, so let me now switch gears. So that's all particles, but you also create beams of light, which is also very fascinating. How do you produce beams of light? It produces from charged particles. The charged particle is charged because there's something special in it. Neutral particle does not emit light, no matter what you do to it. So a very simple theory tells you that virtual light or virtual quantum is trapped within an electron or a proton, and when you shake it hard by a magnetic field or bend it very sharply by a magnetic field, you try to peel off that cloak of energy around the electron and make that virtual light real. So this is an example of electron oscillating in a periodic magnetic field, and you slowly peel off this charge. Interesting thing, when you see the light just coming out, you don't see the electron. And when you see the electron completely coming out, then you don't see the light. In between, you have this entangled light electron state where it's called the formation length of radiation, and that is a subject of great study for now. When the electron is stripped of its properties, then it does not have any attribute. So it takes some length of time to draw energy from the vacuum. Quantum mechanics tells us that the vacuum is not empty, it has a lot of fluctuations and energy reserve. So it takes some time to draw energy from the vacuum, dresses it up, and then it can radiate again. So it's a very fascinating dynamic between light and particle. Here I give an example of how it's produced. You take a periodic magnetic and you send an electron beam. You see it's coming here. You see it's being shaken right and left by the magnetic field. As it is being shaken, light is trying to come out. And of course, light goes faster than any ordinary particle. So you'll see a plume of light in front of it, going ahead of the particle. And if you produce sufficient number of it, the plume can be again separated from the particle, and you get the electron beam out and the light out, and you get light. The interesting thing is that depending on how hard you shake it, how much you shake it, how fast, how frequently, you can change the color of the light, intensity of the light, and polarization of the light. If the electron is going this way, you get one polarization. Electron is going this way, you get another polarization. Electron is going like a spiral, you get a circular. So you can get circular, linear polarization, you can get different colors of light, light that you can never get from nature. So you can tailor pulses of light from a charged particle beam. And here, let me just, this is already started. So if you look at slow motion, red particles are electrons. It generates photons once in a while. Photons, light creates a field which bunches the electrons. The feedback loop goes on and on and on, and eventually it saturates and you get the light. Let me play this again, because this thing cheated me. I was talking too much. So this is it. Here you look at how it's produced. Again, it's very interesting. A lot of physics goes into it. So here is the oscillation of the electron coming in. And in the big picture, you see the light plume going ahead of the electron, because speed of light is faster than the electron. And then you peel off the two and you get the light. And if you look in slow motion in microscopic, look inside the electron. Electrons are in red, light particles are in white. So you see this beam being oscillated by the magnetic field, and look at slow motion. Every once in a while, 100 or 200 turns, because the coupling of light to electron is very weak, so 1 over 137. So you get every 100 or 200 turns, one single particle of light, that's white. You see this coming out. You see electrons, and you see a particle of light here and there coming in. When you have enough number of them, they generate an electromagnetic field, which bunches the electron beam even more, which emits even more particles of light, which bunches the electron even more. So you generate a feedback loop, which is positive. And eventually, you have extracted as much energy out of the electrophoton as you can. It saturates, and then you extract the light out of the electron beam and use it for whatever scientific enterprise you want to use it for. Okay? So it's a fascinating subject. Einstein said in 1916, for the rest of his life, he would try to understand what light is. And even today, we don't know the character of light coming from a single charge in that process of disentangling from a single charge. It's a very fundamental topic. So people have built these large machines around the world. You know, even there's one in India, Indore. They have a light source there where they produce a synchrotron, and they produce all kinds of light. It's a big business. All over the world, you see these little rings going on. It's very useful, because this whole business of X-rays and light started with X-ray by Röntgen. You see him, you see the image of his wife's ring. You see Venke, who got Nobel Prize for looking at structure or ribosome through synchrotron light. And I forget the name of his two collaborators, one from Israel. Yuval knows the lady. Anyway, and then you can actually make molecular movies by looking at, if the electron light is too short, you do not necessarily destroy the sample, organic sample or biological sample. So you get a snapshot of the molecule, and you make a movie out of how molecular dynamics works. And you can store it, you can understand all. So it's a very useful tool. It goes far beyond an ordinary laser, which is a fixed laser, or lasers depend on atomic transitions, and there are only so many atoms that you can use to laze. But here it's free electrons. You can change its energy. You can change the magnetic field to shake it at will, and so you can actually get it done. We can also understand the thermodynamics of biology is very different from the thermodynamics of large-scale engines. So molecular motors and biological engines are being studied by this. One fascinating thing I will tell you, that protein folding. Protein is the engine of life. When you take a protein molecule and you stretch it stretches up to a meter. Then you let it go. Come back to 1 micron from a meter. But in the process, it does not go through arbitrary coiling. It goes through only 5 or 6 different topological geometries. It forms a sheet, or it forms a helix, or it forms. Now, depending on in what geometrical topological shape it landed on the cell, tells you the biological property of the cell, whether it's a liver, or it's a kidney, or it's a heart, or whatever. So understanding this protein folding in situ on the cell membrane by beams of light is very important. So imagine a protein stretched to 1 meter, and you inject. So you actually inject a coiling motion, and you look at the 2 different points in this large molecule, and you look at how they evolve with time. Different types of topologies go into it, and eventually You look at 1 microsecond, it's folded up in a certain configuration. So what you do is look at the correlation of 2 particular points in this large molecule, and you see how they evolve experimentally by your techniques. And what you do is you actually inject a big pulse of light that simulates coiling, like you have an earthworm, you touch it in the tail, it starts to coil up. So you start to do that, and then you actually send very precise pulses of light to probe the correlation between the 2 dots. And then you again inject a pulse that induces coiling. Then you again send these pulses of light. And this way, you create the entire landscape of the dynamics of protein folding in situ, in real life, as it folds onto a cell membrane. Now, I must tell you that quantum artificial intelligence and machine learning is used very heavily for protein folding studies by computer. But these are denatured proteins. They are not proteins in biological action. So studying protein folding in vivo is very difficult. So hopefully this technique will work someday. So this is another use of the folding. Okay. And I can go on to the mapping of the brain, functional mapping, physical mapping, neuronal collapse. You can make a structural image of the brain. You can also make functional image of the brain by looking at magnetic field of the neuronal flashes. You can look at low energy biological excitations. Here is a picture of a brain. The right half and left half hemisphere have different functions. Analytic executive power of the brain. On the one side, an emotive, intuitive power. On the other side, you can also locate tumors by light and also put energetic beams onto it to take them away. You can ask various aspects of intelligence, as you know, by looking at functional aspects of different parts of the brain. Here is just a image of the brain, tensor image, they call it, functional, looking at very weak magnetic fields by magnetoencephalography and a beam that comes in to induce the particular biological action. Let me end this before the scientific part saying that so far we have been looking at particle beams, laser beams, and this, when combined with what you observe by telescopes and radio telescopes and what's going on in the universe at large, you actually get a picture of, 13.8 billion years ago, there was some kind of a unique event. Probably space-time was emerging. Probably there was a gravitational wave that is still there. We know that the universe was very hot and it has cooled down. Today, the temperature of the universe cooled down from huge temperature here to today is something like 2.7 degrees Kelvin, which is minus 270 degrees Celsius. Okay? And it's still cooling down. And what's more, all this stuff I talked to you about, quarks, leptons, neutrinos, Higgs, this is just a small part of the visible world. In order to make sense of what we observe by accelerators and by observation cosmologically, you have to say that only 4% of the matter is what I told you, a standard model mandala. Remaining 25% is dark, is matter which interacts gravitationally because we see it in the motion of the planets. You have to involve their existence to explain how the structure was formed in the universe. And you have to postulate a large amount of energy, 70% of energy which is dark, which is causing acceleration of the expansion. Without these two, you cannot explain this model. So how do you probe these? Okay? And so that's another big issue. The problem is this dark sector, which is 96% of the universe, which we do not know anything about. We only know 4%. It is gravitationally active, but everything else is almost zero, very weak. No electrical field, no electrical effect, magnetic effect, radioactive effect, nuclear effect, nothing. So they're very weakly interacting. So here I have an example for a high school student, how difficult it is to see a weakly interacting. Imagine two pendula, okay? So the standard model universe, which is all these particles there strongly interacting, we can see them, but this dark sector, dark matter, dark energy is very weakly coupled. So let me give you an example. When you take two pendulum, and I have to probably start it manually. imagine, yeah. So imagine this is a weak dark matter which you don't know, and it's oscillating, and it takes a large number of oscillations before it transfers its energy to the other oscillator, which is the ordinary matter. And it picks up slowly, slowly, and you'll see the right, that pendulum will come to a stop, and then the left one will pick up all the energy, and then eventually the left one will stop, transfer back again to the right one. So you need something that rings for a long time. We call it technically high Q devices. Superconductivity rings for a long time. The superconductivity helps to detect dark matter. It looks something that rings for a long time, very weakly coupled. You have to have a lot of patience, a lot of sensitivity to actually find dark matter. Okay, so this, now you see it is going to stop the left one, pick up the right one. So let me go to this one. Within one or two things, it transfers to the other one. It transfers to the other one. I have to charge it again. Let's see if it goes here. See, within 2 or 3 things, transfers. So ordinary matter is easy for us with all the tools we have, because you can transfer, exchange so quickly between oscillators around the world. Everything is oscillating in the world, whereas this dark matter is very, very difficult. So that is the frontier of particle physics, astrophysics, cosmology. Either these objects we call dark don't exist, it's just an experimental observational flaw, or they exist, and then you have to explain them and measure them and sense them. So this whole enterprise, I'll just end with collaboration, could not have happened with great scientists sat in their table and found out great concepts, which were utilized in the large facilities, measurements. You can see entire globe was involved in this process. And the second thing to realize is that the technology collaboration across also is very important. So global collaboration, large-scale collaborations were important, and technology, starting from superconductivity, which I told you, new types of materials, new types of superconductors, and then now atomic techniques and quantum techniques are coming into being, and the basic goal is to find new particles, new forces, new processes, and what is this dark world that we cannot explain, but seem to see gravitationally, but cannot see them otherwise. And talking about collaborations, let me give you an example from superconductivity. Is a great example of collaborative behavior in matter. If you look at a wire, electrons going through, I got this slide from my friend Wolfgang Ketterle at MIT. Electrons wants to go to create a current, but if you have an impurity, electrons collide and they impede the motion of the electrons, which causes resistance. Yeah? Now what to do? Now electrons decide to gang up on this impurity. They just say, we want to act collaboratively, gang up, so that this impurity has no chance of obstructing us. So they gang up, phase up, all in phase, and bang they go. So you can imagine that this is the kind of the electron cloud becomes like a superfluid, has no viscosity, and nothing can stop this super zero viscosity fluid against a target. So you can imagine these electrons to be people, superconductivity, superfluidity of charge. Whether you have a coherent program or not depends on whether different partners team up properly in phase. I give you an example from dance. If you look at a modern dance, right, you look at atom pairs for superfluidity, or Cooper pairs for superfluidity, or matched collaborators in science, like a big lab and a big lab, or a small university and a small university. I just use gender here, which is very inappropriate probably, but anyway, it's male and female. You can use whatever you want to use to show polarities. But what if there's more of one type than the other? There's excess men. Do you stop the dance? That means the entire phenomena of superconductivity quenches. It stops. It does not. It's not a superfluid, because you have stopped the dance of the collaborative dance electrons. What happens if you let the excess men leave, but keep the dance going with the rest of the people who are matched up? That means you're excluding some number of people from the dance, which is not good either. But what if you are smart and you invent a new type of a dance where you don't necessarily have to match up, but it's a higher order nuanced correlation between partners. And this is so important because when CERN collaborates with India, collaborates with ICTS, the Raman Research Institute, IISc, Germany's famous lab, America's big lab, they're all different partners with different strengths and stuff. So you have to learn a new type of a dance. You don't have to be matched, but you have to have a new type of a collaboration where everything works. So all the new superconductors that people are finding today, beyond old ones like niobium and stuff, they all have very higher order correlated effects. So we can learn something from this example. Now let me talk a little, we talk about dancing, right? And this entire metaphor of particles, energy, matter, and cosmology, this is just a metaphor, the best way we can describe the world. And it's a dance of different forces of nature. And in my house, I have a little dancing Shiva statue, Nataraja. At CERN, there's a 3-story high statue of CERN. It's the only statue at CERN. It has 2 significant facts about it. One, it marks the friendship between CERN and India. India is a not at all matched partner to all the other European countries, but they think it is important enough that they put this statue as a gift of Government of India to CERN. But second, it captures the cosmic dance of space and time and matter and energy and creation, destruction in a beautiful way. I cannot describe it, but let me play a 3-minute video of Aldous Huxley, who described the dancing Shiva in 3 minutes, and you will really enjoy it, I'm sure.
We have such bad symbols. I mean, we really no great symbols now. All that we have are these ridiculous nationalist symbols like flags and swastikas and whatnot. But no sort of great cosmic symbols. I mean, when you think of the staggering symbols that the Indians produced, I mean, the dancing Shiva, for example, we never produced anything as comprehensive as this. The dancing Shiva, those little bronze statues. It is the Shiva with 4 arms dancing with 1 foot raised. And, well, I mean, I go into the details. They're really quite extraordinary. It's the figure stands within a great circle, sort of halo, which has flames going out on the symbols of flames. And this is the circle of mass, energy, space, time. I mean, this is the material world. It's a great world of the all-embracing material world with its flames, with the energy. Within this, Shiva dances. He's called Nataraja, the Lord of the dance. And he dances, he's everywhere in the universe. I mean, this is his dance. The manifestation of the world is called his lila, his play. I mean, he sends his rain upon the just and the unjust. And he's beyond good and evil, of course. It's all an immense manifestation of play. He has this long hair, which is the hair of the yogi, contemplative, and it streams out to the limits of the universe, you see. Therefore, this sort of yogic knowledge of this contemplation includes everything. He has 4 arms. In the upper right arm, he holds a little drum, which is the drum which summons things into creation. You beat upon this drum and things come into existence. In his left arm, he holds a fire, which is what destroys everything. He both creates and destroys. His lower right hand is held up in this attitude, which means be not afraid, in spite of everything, it is all right. The other hand points down at his feet, and 1 foot is planted squarely on the back of a repulsive dwarf, this infinitely powerful dwarf called Muyalaka, I think his name is, who is the ego. And he has to break the back of the ego, you see. What he's really pointing at is the other foot, which is raised. And this means this foot is raised against gravitation and is the symbol of spiritual contemplation. The whole thing is there, you see. I mean, the world of space and time and matter and energy. the world of creation and destruction, the world of psychology. I mean, how do you get out of this? I mean, if you don't break the back of the ego, you're lost. And if you don't practice contemplation, there will be no liberation for you. I mean, we don't have anything remotely approaching such a comprehensive symbol, which is both cosmic and psychological and spiritual. I mean, it's really most unfortunate that we have such miserable symbols.
Okay, so by the way, this ego business, he talks about the Nataraja crushes the ego. So the ego plays a big role in scientists. I mean, so you have to have an ego, because otherwise you don't feel you are doing anything. You are discovering something new, or you are contributing to the development of science. At the same time, if the ego gets to you, it becomes very destructive, competitive, and all of that. So in this game of large-scale science, you have to learn how to be part of a big team. So you have to kind of give up a lot of your identity as an individual. At the same time, keep it sufficiently so you can feel that you are a major player. So that's a very highly evolved sense of your identity. That's very important. So most of the time when you look at things, it looks complicated, and you begin to see little symmetries in there. And eventually, when you work at a problem long enough, you just throw away all the essential complications, but keep just the essential features of the pattern. And so physics has been able, astrophysics, physics, science, engineering in general, has been only able to get some of these internal patterns right, and there's so much to explore. So I'll end with a little piece of music. Most of you will recognize this gentleman. This is Bose-Einstein Bose. He used to play S-Raj. I got a piece of his music, and I got it transposed into violin. So the background music is not Bose playing the S-Raj. It's somebody else playing the violin based on a composition that Bose composed for S-Raj. So it's a nice piece of music. Anyway, let me finish by these inspirational words of people, and then thank you for tolerating 50 minutes, and I'm open for questions from you. Oh, come on, it's okay, you got it. Oh, no question is simple or stupid. Every question is meaningful, so don't be shy.
Questions?
Yeah, there's a question.
So, can you use the electron beam to activate a biological cell and study what's going on inside and outside?
Yes, I think they're doing it in Stanford and I think Daisy in Hamburg. But you have to have very low energy electrons
Because
for that.
we
You
can
don't want to destroy the biological properties by energetic, too high an energy. You have to excite the biological function, but not kill. Yeah, so very tricky. You can do it.
What, like for COVID-19, it's the cell surface is what is what's going on there to know how the COVID virus is knocking it out. Can we study that?
So I'm not an expert on the virology, but I know that as soon as COVID came on in February 2020, and then the biologists and the physicists at Fermilab, Stanford, and Daisy started this program, and I don't think they have made much progress in actually penetrating anything, but eventually they probably will. Yeah. Yeah. They already work with this, what is that company that made the Indian vaccine from, what is the company in England? AstraZeneca. So AstraZeneca produces designer drugs. So they put some molecules inside other cage molecules to make designer drugs. So we know how to put molecules inside a cage of a molecule specifically for designer drugs. So that same technique can probably be used for understanding other things.
Hello, sir. My name is Ishan. I'm an undergrad student. Sir, I have a rather general question. And basically, sir, if we see today, we have matters going on and things, people are saying things about string theory and other aspects. And we are all, whether it be the particle physicist, the experimental physicist, or the theoretical physicist, we are all looking for a single theory of everything that we dreamt of. So, sir, in that aspect, sir, why don't we look off as a universe, as a topology? And this idea came to me since it's based on two reasons. First of them is like, so since you have also said that there is some of the area of the universe which is so-called dark matter, which is influencing the things but is not detectable. So probably it is maybe because of that topology which is not being taken into account. Or one more thing that I would like to quote that I just saw a few days back. In 2010, Stephen Wolfram, who is I think the founder of Mathematica and Wolfram, which is one of the most popular softwares we use, and the most costly ones also. And he was telling that actually his main aim was not to build Mathematica as a search engine. His aim is much longer, and his aim is also towards theory of everything. And he was basically showing us that using numerical techniques, we could candidate out the candidate universes, topologies that we could use in order to test our theories and make our work simpler as theorists or experimentalists. And sir, the third reason being, sir, like as I ask this question to many people, but all they do is laugh upon me. But I don't understand why they laugh. And I've studied quantum mechanics on my own, and I saw that spin of any elementary particle, except Higgs boson, every particle has a spin. So spin being characterized an intrinsic angular momentum. Everybody knows that there is an experiment called the experiment in which the beam was shattered into two parts, and through that experiment we know that electron has a spin, but no one has tried to explain what is the theoretical basis and reason for the spin. And according to Sir Roger Penrose, he told that this has been quoted by him that like gravity, unless gravity is included into quantum mechanics, quantum mechanics is completely inconsistent. So, sir, I want to just hear your remarks on this.
Is it three things or four things? I forget now. Let me go with the first one.
Yes, sir.
You can sit down. You can sit down. Yeah, so you are absolutely right. We can learn from what's going on at large to know about. This is why I am embarrassed as a particle physicist after 40 years of understanding the standard model. And these cosmologists are telling us that you are only dealing with 4% of the universe, 96% is dark. I mean, how embarrassing could it be, right? So we learn from that cosmological observation. And string theorists and other particle theorists, they are working on string cosmology and understanding what could be the fundamental topological structures of space-time, or without space-time, basic mathematical topologies which will generate space-time from fundamental. Space-time will emerge as something second order. It is not given because space-time was emerging. So that people are working on it, you are right, and we do not know how to connect it, but there's a lot of work going on already. Second one is Stephen Wolfram, who is actually my contemporary. He's a great smart guy, and yeah, he's not spending much of his time on Mathematica. He has a theory called theory of automatons, cellular automatons, and he's trying to explain quantum mechanics and field theory, strings, everything with this theory of cellular automatons. And his approach is numerical, meaning it's like artificial intelligence that you do not really understand how it works, but it somehow learns from patterns and then applies it to solve a given problem and gets the solution. But if you want to understand it into ordinary framework of how things evolve, you have to go through the steps of how did it decide to go this path, not that path, and you will not normally take the path that the AI takes. So a lot of work is going on in that, and I'm confident that theory combined with AI type of applications on numerical understanding of nature will go a long way. But it's too early to actually say anything about it. And progress is very slow, but he has a point there. Third thing is spin and Roger Penrose and all that. So, you know, a particle has a property like charge or spin or mass. And we do not think these are today with quantum advancement and quantum entanglement and stuff. These properties may not be as permanent as we think they are. For example, we are trying to do an experiment. We have an electron beam and a positron beam. Electron has negative charge, positron has positive charge, but they both radiate. But the radiation does not know whether it's coming from a negative charge or a positive charge. But it's coupled to the charge. So if you can somehow swap the radiation from two beams, the clouds, which are entangled with the charge, but you swap them, you can get an electron acquire the charge of a positron, and a positron acquire the charge of an electron. The question is, how would you know that you have done it? Unless you have some other parameter that tells you that they are different, like spin. Spin is not a good idea, because spin is connected with magnetic field, angular momentum, charge, all of that. Some other criteria. So that means that properties like charge and spin fundamentally are not explained by physics today. We just take it that they manifest as a certain behavior in a magnetic field or electric field. But if you really ask, what is a charge? I cannot answer you. What is a spin? Except that it behaves in a certain way in a magnetic field. Its intrinsic nature, I don't know. So it's a true statement. I don't know that. Fourth point, Roger Penrose, I fully agree that two approaches to unify what we know about standard model, which checks out electricity, magnetism, radioactive decay, and how does stable matter form, but does not take into account gravity. And string theorists are trying to say gravity must be brought to this model to comply with us, then you have quantum gravity. That's one approach. Other approach is called loop quantum gravity. They say Einstein has been right, gravitational theory has not been proven wrong, quantum mechanics is incomplete, because it does not take gravity into account, modify quantum mechanics, including gravity, and bring it to. And that's Roger Penrose. Okay? And ultimately, what scheme would actually work, combine the two, we don't know. But I think this is a very valid point. If you look at two particles, quantum mechanically acting, they have totally different space-time manifold. This particle is seeing a totally different space-time, this particle is seeing totally different space-time, and quantum mechanics of all these things I'm talking about does not take into account that, because its effect is supposed to be very, very small. But when the entire world was very, very small, then you have to take into account that gravity. So no answer to it, but it's a very valid question. Okay. Yeah.
Yeah. Thanks very much for this broad and thought-provoking talk. One of the intriguing statements that you made touched upon the schism between those who believe that leaps in science, should I say quantum leaps in science, are due to new instruments, as opposed to those who think that these are due to new concepts or new ways to look at things. And I think it would be very interesting to bring here at some point a historian of science that will give a perspective of where the big developments came from. You can imagine that I have a different opinion for yours, but
no, I don't have
think
any
it's completely open.
I fully agree with you. I think it's a dance between the two. No one has a superiority. We depend on the quantum mechanics. You know, it's a marriage between experiment and fantastic theoretical concepts like Heisenberg's principle of relationships and not fantastic. But I think it's a play between the two, absolutely. Yeah. There's no superiority of experiment. Oh, yeah, there's a question.
Hello. So I'm a computer engineer. So in my field, quantum theory has been adopted and it's still under research, but a lot of companies are betting on it. Big companies like Google and Microsoft in quantum theory. So far, for the past 50 years, we've been using what physics has helped. Basically, the invention of semiconductors and large-scale integration has led to...
My talk still here?
Sorry?
Yeah, go ahead.
Yeah, so...
No, I have a few more slides, yeah.
All right. So for the past 50 years, we've been using like fixed finite states, zeros and ones, which are basically like not quantum. And these discrete states have led to all the inventions like laptops and phones and watches and all that. So, but right now, a lot of companies are pitching into quantum theory and how superposition can help to solve bigger problems, like optimization problems and all that. I'd like to know what your take on is it, because I haven't seen any feasible or any useful results so far. I just want to know your take on it and how far this is feasible.
I can give you my take. There's also Yuval here who works on quantum information and steering. But look, when you had classical physics, Newton, Maxwell, Faraday, quickly engineering took on and made devices out of it. And Lord Kelvin actually had a company, a power company of selling electrical products. But quantum mechanics, 1925, 26, and this is 2022. And we have been studying fundamentally, using it in experiments and conceptual theory, but not a single quantum engineered device has been fabricated. And now, in the last 10, 15 years, people are realizing that you can actually exploit quantum mechanics, entanglement and all of that, to do more than what a classical object does. And I believe in it. I think there's a lot of hype in this game. But the basic fact that if you take a classical computing on bits, 0 and 1, or plus 1 and minus 1, in a quantum mechanics, that becomes just a vector which can go around a surface called a Bloch sphere. So instead of just 0 and 1 or minus, it can move the entire surface of the Bloch sphere with infinite possibilities of phases. So clearly, you can create a computational program that is much more capable than a single classical bit. So qubit, as moving on a Bloch sphere, is much more. So, but we do not know yet how to engineer proper combination of qubits, how many qubits you want to entangle. So people have done 10, 15, maybe 20. I don't know the most result. People are trying the 3 or 4 technologies that are using ways to entangle things. Superconductivity is one example. Then one uses trapped ions is one. So there's various. So I actually launched this program in USA in 2016, that quantum computing may be far away, quantum information may be far away, but China has already entangled a photon here and into a satellite. India has now done it. So clearly, communication quantum mechanically distant objects is now an engineering success. So on the way to a quantum computer, you have all these quantum sensors that you can use to detect particles and waves. So a lot of fundamental low-hanging fruit. So they created this program. It was not easy because we had to bring Google, Microsoft, all the companies. They signed off on it. Google created a quantum lab in Santa Barbara. And so it is going slow. People are talking too fast about it, but I'm sure it will make progress as time goes on. That's my take on it. I had 3 slides on that, but I deleted them for some reason that you would not be interested in it. But a picture with all the Google, Microsoft CEOs sitting there around physicists discussing whether there should be money put into quantum or not. So India has $800 million worth of money sitting in Modi's desk for quantum initiative that we still do not know how to put program into it. Hopefully, Bangalore will play a big role. So I'm trying to help the Bangalore Institute to do that. So I'm optimistic.
Yes, sir. Thank you so much for your talk. It was really, really delightful. I want to understand what entanglement is. If you could
What
entanglement
Oh
is.
boy.
Like as simple terms as possible.
Wow, there's another big talk on the topic. Entanglement is basically, if you create a state where you can identify kind of two entities participating, and they're initially in a state that talks to each other quantum mechanically or whatever, and quantum mechanics says you do not really know what's outside the world until you actually look at it. So the ontology of quantum mechanics is empty, but the knowledge about the system you know already from the dynamics of the quantum mechanics. So then if you just kind of artificially separate the two, and then you do not know really which one is where. But the moment you look at one of them, your knowledge updates itself saying that it is not in the other one. Okay? And same thing is the property. Like if two things are joined together and they have a joint property, one has something going up, one has something going down, that relationship is preserved no matter how you separate them. So just because now you have knowledge of one does not mean that you are actually sending that information to the particle. The system already knows it's entangled. You are simply updating your knowledge about the fact that, oh, you find this particle in this state, so that one must be in the other state. So these people get very confused about that signal is being transmitted from one to the other, they're entangled. They're entangled quantum. If you think about it, quantum 13.8 billion years ago, everything was into a narrow point of 10 to the minus 43 centimeters. You, me, sun, galaxy, everything was there. And there was gravity. There were all the forces, electric, magnetic, and they're all into one little 10 to the minus 40. They're talking to each other, and it is its own character, right? You do not just throw away that character by simply expanding and nucleating into the whole world. Unfortunately, that information, which is quantum mechanical in nature, gets diluted by external noise and everything. So to discover that entanglement is impossible from the Big Bang. But locally in a laboratory, things are entangled, and you can actually do experiments with it. So it requires a big talk. I probably did not do good justice to it, but an expert here sitting, Yuval, so, but in that part it is, yeah. Basically, I think everything in the world is entangled. We just do not see it because so much time has gone on that things appear to be separate.
So recently I ran into a discussion where someone was claiming that through quantum entanglement, like if I happen to separate two particles which were entangled by, let's say, a light year or something, that by altering the state of one, we could be observing like a change in the state of the other.
No,
so
you don't change it. You just get knowledge of the other one to be whatever it is.
So someone was claiming that this somehow could be exploited to create a method of transforming information faster than light. So how valid is that claim, sir?
I do not think of entanglement as signal transmission at all. It is just you're updating your state of knowledge about the system. Your state of knowledge, it could be this way, that way, this way, this way, that way, that way. It could be any one of those. But you discover that one thing is this way, that immediately updates your database out of a menu of various possibilities. This one already tells you what the other one could be. There's no need to transfer information between the two. Einstein was bothered by this very much because he believed in objective reality, that whether you look at something or not, it exists, right? So, he's made the famous question, the moon is there whether I look at it or not, right? Right? That's objective. So that is called local realism. My left foot is my left foot, and my right foot is my right foot. They exist independent of each other. If I look at my left foot, it does not change my right foot. So that's local realism. It breaks down in the quantum domain. It's just not true. Local realism is not supported by experiments. People have done best, and these guys got Nobel Prize, right? The three guys, Clauser, Alan Aspect, and Zellinger got Nobel Prize for doing experiments a few decades apart to show that they did experiments to show that local realism is not respected by quantum mechanics. So that intuitive understanding of classical world breaks down in the quantum world. It took Schrödinger a long time to come to it because he still did not believe in jumps. He was still talking wave equation. Heisenberg was saying all that matters is the relationship between transitions. He created a matrix of transitions and energy, and he created an algebra that explains quantum mechanics. Schrödinger was saying, these damn jumps. He wanted to explain them by wave mechanics, an eigenvalue problem, which became difficult for him. Eventually he accepted that mechanism. So this business of momentum and position and position and momentum, they are not commutable. If you observe position, then you observe momentum. And if you do first observe momentum, then you observe position, you don't get to the same point. There's a little difference by Planck's constant, h. And that is the commutation relation, that famous contribution of quantum mechanics. So, and that is not supported by classical physics. So.
Sir, what is the real reason of superposition, and how it can affect the energy or radiation which are emitted by the electron?
Yeah, maybe you can, if you can take this up and yeah.
What is the real reason?
Far away from you. Right.
What is the real reason of superposition?
Real nature.
Real reason.
Real reason
for superposition.
Oh, okay. So, many ways you can think about it. Mathematically, if you describe the world in terms of differential equations and stuff, they are linear. Meaning you have one solution, you have another solution. If you make a superposition of the two, they work. That's also a solution. So like Schrödinger equation is linear. Meaning if you find one solution 1, another solution 2, if you take some number times 1, some number times 2, that is also a solution. So that's because the equation is linear. But if the equation was not linear, fundamentally, then you don't have to have superposition in that sense. Now, whether the world is fundamentally linear world, that's a different question. Okay? But the nature of superposition is basically when you have a linear system like that, then you can interfere them like a light, beam of light. If you take the wavefront, okay, and if you split the wavefront into two, and then you bring them combined together again, because Maxwell's equations are linear, you get interference pattern of light fringes and diffraction, all of that.
What is the environment that we can see the superposition?
And in quantum mechanics, you see the interference of matter waves. Matter is also a wave. So if you interfere the waves, you see fringes, meaning density of matter, dense and light and dense and light. So you can create interference of a particle beam by the interferometer. Atomic interferometers, electron interferometers by slits and stuff like that.
But when we are detecting the electron, it doesn't wave like wave, no, sir.
Well, if you look at it, then it goes away, yes. If you look at which slit is going through, then the interference pattern, that is the typical, that is the weirdness about quantum mechanics.
Thank you, sir.
Just building on that gentleman's question. So if two particles are entangled and they are at whatever distance, can you manipulate one of them and the other hence changes its states based on how you've manipulated one?
Not manipulate. I would say that if two particles separate, you measure one, and let's say you are John, I am Jack. I measure it. I say, hey, this is up, right? And then you don't even have to measure it there. You know that it is down, something like that. That's the entanglement. But if you don't know, nobody has measured, you don't know which way, or somebody has to measure it, and then the other one.
But say, can you or I manipulate the state of one? And then...
This is called quantum steering. We have an expert here, Yuval, who stood up in the light blue T-shirt, he is now working on how you can steer a certain quantum state by very weakly interacting with it, and by several nudges, you can steer a quantum state to a certain state. So this is the quantum engineering now. That's what he's working on. So yeah, it's probably possible. Its ultimate limit, we don't know. But it's quite possible to steer a quantum state by very weak measurement. By strong measurement, you force it to be one or the other, but very weak measurement can do it. I hope I explained your, yeah. He gave a talk yesterday at IISc, which was a very enlightening talk. Right.
Any more questions?
So this last thing I talked about, identity of a particle, in a way, it's like you know the story of Cheshire Cat by Lewis Carroll, where these cats, long cats in the north of England, and this girl sees this cat, and this cat is a funny cat, it has a grin, smiling at the girl, and you look at it long enough, and the tail disappears, the body disappears, then she sees the cat has gone to the other branch of the tree, but it left its grin where it was. So the cat has left its grin. So it's called a Cheshire Cat, right? So particle and its property, now people are doing experiments to see whether one can separate a particle and its other attributes, position and anything else, from its one attribute, let's say spin. And the photon leave its spin there somehow and be detected here. That's called Cheshire Cat experiment. So this electron-positron experiment I talked about is a Cheshire Cat exchange of charges, electron and positron. You are taking advantage of the light that comes out of one and the other. They are entangled with the actual charge, but you somehow swap them, and then one's charge, smile, is transferred, exchange for the other's charge and smile. And then you have the exchange. So identity is not is a classical concept. Quantum concept of identity is now being challenged by these things. And a lot of it is because we take space and time for granted, and physics depends on symmetries of space-time, rotation, reflection, translation, all of that. But if you do not know the dynamics below space-time, then of course you will find all kinds of inconsistencies. That's what I believe. I mean, if you look at an atom, before it is ionized, any energy you take of the hydrogen atom ionizes at 13.6 electron volts. If you sit just below 13.6, you find a finite number of states in which that atom can exist, right? But you can rotate the atom continuously in space. So these two things, the continuous rotation of an atom and this finite number of states, forces you into an argument that probably existence of an atom in eigenstates, fixed states, is probably probabilistic. That's what quantum mechanics is, probabilistic. It never tells you a definite answer. Says this is the probability of seeing this is 40%, seeing that is 30%, and seeing that is 30%. It never tells you exactly what you are going to get. And that's because of the inconsistency of space-time symmetries and the fact that the world is quantized. So, you will find as many opinions on this topic as many physicists. It's very controversial interpreting quantum mechanics. So, but it's a fascinating topic. Hey, it's a hot session, a lot of questions. It's great.
Thank you for your talk, sir. But my question is, can we hypothetically discover a particle?
Yeah, just hold it closer to your mouth. Yeah.
Can we hypothetically discover a particle which can travel faster than light?
Can you create a particle traveling faster?
No, we can discover it. Maybe
discover it?
In a particle accelerator.
We have not been able to so far.
Can we in a future maybe?
I mean, there is a theory that allows faster than speed of light particles. They are called tachyons and things like that. I am not an expert on it, but as far as I understand, that world which allows particles having faster than speed of light, they have a lower bound. Particles cannot go below speed of light. And our world is the world where particles cannot go above the speed of light. And these two worlds probably are not coupled, or they cannot be reconciled.
But can it be, coupled or linked?
I don't know. I don't know. At some time ago, there was a claim from CERN. People have seen neutrinos going faster than speed of light. That caused a lot of buzz and turn, but ultimately turned out to be an experimental error. So I can. You never say no, you know, but I think it's very probably knowing what we know today, probably unlikely that we'll see it. But we do not know everything about the world, so incomplete. Right? How many of you are students, by the way? Wow. Wow. And how many are professional physicists or interested parties outside? Oh, there are a few. Oh, that is fantastic. That's probably 90%, 95% students. Great.
So we have some questions from YouTube. When virtual photon dissociates from the electron, does a new virtual photon associates with it?
Say that again?
When virtual photon dissociates from the electron,
Yes.
does a new virtual photon associates with it?
Yes, that's what so electron becomes stripped of its attributes. It's called a bare electron. And then it takes some amount of time for the bare electron to draw energy from the quantum vacuum and raise itself up and become virtual. And then it becomes a charged, dressed electron. Yes, possible. Can you, the chat, you can probably project it. No? No, that's...
Know what is happening in the brain.
Is it possible to?
Is it possible to probe the brain and know what is happening in the brain?
Probe the... I didn't get it.
Probe the brain.
Brain and no?
What is happening in the brain?
Yeah, so people do that all the time. I mean, so brain has chemical signals, electrical signals, and magnetic field signals. So magnetic field signals you can detect by having a magnetic helmet, and it is called magnetoencephalography. By looking at your mood, happy, sad, angry, depressed, hungry, you can actually change the magnetic field pattern and measure it without probing into it, but looking at just the magnetic field. And chemically, electrical and chemical signals are always monitored in laboratories of neurosurgeons and neurologists and stuff like that. Yeah, it can be done.
So we have one more question. Is Wolfram's physics project doomed to failure unless Wolfram realizes the importance of Milgrom's mount?
Importance of what?
Milgrom's mount.
What is that? Milligram. Maybe somebody who is very specialized. I don't know. Do you know?
Milligram was like that 6 degrees of separation thing he had. There was an experiment that's the Milgram experiment. It's more of a social experiment that like people are connected by max 6 degrees of separation.
I see.
So I mean, if he's referring to that, so I don't know. I mean,
do you know the answer to that?
No. Answer I don't know. The Milgram thing, I mean, is probably that, but I don't know how it fits with the question.
I don't know the details of, what is the, this is a very specialized question. So what is this effect?
Milgrom's mount.
I do not know that particular thing that you explained, but Stephen Wolfram's cellular automaton has many versions of it. And one version is even being propagated by famous physicist Gerard 't Hooft, who got Nobel Prize in physics for QCD. So I would not throw away something from Stephen Wolfram so lightly. But this particular question may be relevant. I do not know this particular thing that he or she is talking about.
So we have one more question. What is the current state of development of Wakefield accelerators?
So the Wakefield, instead of using radio frequency cavities to get electric field, you actually take a plasma. And if you can ionize the plasma and you look at the electric field, very, very high, you can get very, gigavolt or hundreds or thousands of gigavolt per meter kind of field. But the question is, in order to do that, you have to send a laser beam through a plasma or a particle beam through a plasma. And most of the time, the conversion of electrical energy from the wall plug to the laser is very, very poor. And from laser to the plasma is even poorer. And from plasma to the beam. So you have 3 steps. And when you multiply 3 things, even if something is 0.9, 90% efficient, 0.9 times 0.9 times 0.9 becomes a very small number. So most of the times, all these wake field acceleration is promising for very small accelerators like 1 GeV or 2 GeV, not for TeV, because you need several nuclear reactors to support this kind of energy transfer. So,
any more questions? Yeah, we have a small gift for you, small memento. So I'll invite our director for giving away the gift.